this. All right, so when you buy something, an appliance, so let's think about you plan to replace your natural gas-fired domestic water heater with an electric heat pump water heater. What kind of costs are there? Anybody you can speak or type in the chat.
Decrease in your gas bill,
Yeah, so what kind of cost would that be if we could generalize that statement?
heating costs, uh,
Yeah, so yeah, if
cubic.
it's super general, it'd be like operating costs, right? That way you could relate it to anything. So that's one of the types. There's another type of cost.
Your electricity bill, what
Yeah,
would
that
that
would be an
cost?
operating cost
Operating
too.
costs.
Installation, yeah. So basically, the upfront cost, the capital cost. You can't just steal it from the store unless you're really strong and have a giant pocket for a water heater. And then you probably have to pay a plumber to put it in your house. So those would all be upfront costs or capital costs. So you have to pay for it, and then you have to pay to use it. Same with a cell phone or anything else. All right, so capital cost again. How much does the new water heater cost? Annual cost. How much will the new water heater cost to use each year? So I have a picture of like an electric bill there. All right. Okay, so then a good question you may ask if you purchase something like this was how long does it take capital cost investment that saves money each year to pay for itself? So we bought this electric water heater that's actually more expensive than a gas water heater, but we know that it will use less energy and use less money. The electrical bill will be lower than the gas bill. So in a sense, it will start to pay for itself over time. And so you can ask, how long will that take? And so there's a simple calculation where you just take the extra first cost, which is the capital cost differential from what you're buying that's better than what you would have bought otherwise. And that's why there's that delta P symbol. So it'd be the cost of the electric water heater minus the gas water heater. So it's what you have to pay in addition to get that better thing that will eventually save you money. And then you divide that by the annual savings. So dollars divided by dollars per year gives a payback time in units of years. And it'll say like, okay, this water heater will pay itself back in 2 years or 4 years or 5 years or whatever. And so that lets you know how long it takes to pay it back. This is useful when you want to compare it to other investments you could have made with that money, or also in particular, you want to make sure that it pays itself back before it breaks. If it has a warranty for 6 years and it has a payback of 8 years, then that might not be a smart thing to do because it might not ever pay for itself. So it's a good first check, but it's too simple because it does not consider how long different water heaters last, nor does it take into account the time value of money. And this is where things start to get kind of voodoo-y. In physics, mass and energy is conserved, but in economics, money is not conserved. It's worth more now, today, than it is in the future. So there's these little thought experiments that economists do. They say like, well, would you rather have $621 today or $1,000 5 years from now? Can you guys raise hands in Zoom, or is that just cheesy? Let's not mess around with that. Poll. This stuff's.
That's like the fancy hand button that I can do. I don't know if you can see that,
Oh yeah, I can see it.
but
I don't know. This
I
stuff's
don't know
waste
what
of
that
time.
point of that would be.
Okay, who? Oh, I'm seeing some hands. All right. Or you can use check marks too. So who would want $621 today? Who wants $1,000 5 years from now? There's some good savers in this class, but it's about half and half. I think the $1,000 5 years from now won out a little bit. That's good. You guys are optimists. So the economists would say this is actually the same amount of money. having $621 today equals having $1,000 5 years from now, because that 621 that you get today, you can actually use. You could do something useful with it. You can make a purchase. You can make a decision. You can pay rent, whatever. Not in this town, but whereas you can't use $1,000. And so there's this idea that money today is worth more than money tomorrow. And so how might we figure out this equivalence of 621 to $1,000? Well, it implies some interest rate. It implies that if I had $621 today, I could invest it and it would continue to grow until I had $5,000. I mean, had $1,000 5 years from now. And so the simple finance equation, where'd my mouse go? Is the future value of the money just equals your principal, the amount of money you have today, and then invested over time. And this is I, the interest rate. So banks are like, 1% right now or something. Mortgages are like 4%. And so 1 plus that interest rate, so 0.0 something, 0.5 for a 5% interest rate. And then raised to the power of how many times that interest rate compounds. Standard compounding rate would be like every year. That'd be APY, annual percentage yield, or annual percentage rate, APR. And so this would be 5 years. So we plug in a 5 here, and our present value is 621. Our future value is 1,000, and then we could solve for I. And so rearranging this. Okay, I have to talk about this. When you're growing your money, it's an interest rate. When you're devaluing your money, like if you're paying something back or you're trying to figure out what that money in the future is worth today, it's called a discount rate. But functionally, mathematically, they're the same thing. So because when rearranging the function for the present value, which we're doing today, the value I, interest rate, becomes a discount rate. Don't get hung up on that. It's just convention. Okay, so we can rearrange this equation to try to figure out what that discount rate or interest rate is. So that interest rate is going to depend on the future value of the money, present value of the money, and then how many years it's compounded. And this -1 just comes from this one here after the function got rearranged. And so the discount rate equals this fractional term raised to the 1/5 power minus 1 equals 0.1 is 10%. So that's actually a pretty steep interest rate or a steep discount rate. So maybe it is wise to take that $1,000 5 years from now, because it's actually kind of difficult to make investments grow that fast. But at a 10% interest rate, what this statement is saying is that $621 today equals $1,000 5 years from now, because you could have done something with that $621 to make money in those 5 years. All right, so what does this all mean? Let's go through a few examples, some more slides. So here's just different discount rates plotted over time. So years down here, 2013 to 2050. And you have $1 today. Or if you have some money in the future, what makes it worth $1 today? And these are just different discount rates and amount of time. So it's saying that like $1 is basically worthless 100 years from now if at this steep of a discount rate. Interest rate would be the opposite direction; it would go up. But this is for discount rates. All right. Perhaps this graph will help explain things a little better. So the net present value, or the present worth of something today from the future, is going to be a lesser amount because you can use it now. And so if here's today at the beginning of this x-axis, and so if you get a chunk of money a month from now, that's this black line, a current cash flow, say $100. Today, you'd say, I would accept $99 if I could get it today, rather than wait a month and get $100. 2 months from now or 2 years from now or something, you will also get another payment of $100. Say you're a landlord or something awful like that, and so you're expecting another $100 a year from now or next month, and you would say, okay, I know I'm gonna get $100 2 months from now, but I'd be cool with like $90 right now because I could use that right now. And that trend continues. 3 months from now is another $100, but I'd be fine with $60. 4 months from now, another $100 comes in, but if I could get it today, I'd take it for $40. So this is just kind of visualizing that time value of money. There's an equation for this present value of future savings or present value of future income. And so the present value equals the amount you will receive multiplied by this present value function, which is a function of the discount rate or interest rate and the number of times it will be compounded. So again, for a series of n annual $1 amounts that start 1 year from the present value function is the summation of all those present values for each year. And so a year from now, that dollar will be worth $1 divided by 1 plus that discount rate. So say the discount rate is like 10%, it'd be 1 divided by 1.1, which would be like around 0.9. So it'd be worth 90 cents a year from now. And then each subsequent year, it continues to compound. It gets less and less and less and becomes this infinite series. And you can terminate it at any given year or compound rate and do a series analysis, which I will not bore you all with here. That's gross math, to find this series analysis of this function. And so this series collapses down into this function, and this is the present value function. And so you use this to figure out the present value of all those future payments all added together. And what would that look like in terms of today's dollars? And again, just depends on the discount rate and the number of years it compounds. So let's go through an example, and hopefully it'll start to make a little bit more sense, or you can at least see the utility of it, even if it doesn't make sense. And you can still use it like a tool, right? I don't know how a computer works, but I still can use it. Right. So 2 electric lawnmowers are for sale, and they both cut grass equally well for 1,600 hours per year. And man, they are cutting a lot of grass. And they both last for 20 years. The good one costs $2,400 and draws 79 kilowatts. And the premium one costs more. It costs $2,900, so $500 more. But its motor draws a little bit less power, 77.5 kilowatts. Electricity costs 8 cents per kilowatt hour. Assume a 10% discount rate. So let's try to figure out which one of these is the better investment, which has a lower present value, so therefore would be saving money. Okay, so a good one is 79 kilowatts times 1,600 hours a year times 8 cents per kilowatt hour, and so it costs $10,112 per year. So every year we have to pay that operating cost for that lawnmower. Premium, same equation, just a slightly less power draw, and so its operating cost per year is slightly less at $9,920. But these yearly costs are like annual payments we have to make into the future. And that yearly cost 10 years from now might not be as important to me as it is now because of this time value of money. So let's calculate the present value of all those future payments. So the present value of the 2 motors, including first cost and annual cost, is therefore, for the good one, it costs less up front. So here's our upfront cost. And then here's our operating costs multiplied by this present value function, which shows how this changes each year. Again, interest rates and compounding rates. And so this present value function for $1, this is just for $1 when you solve the present value function at first, at an interest rate of 10% for over 20 years is equivalent to $8.5. That's kind of crazy, right? You're getting $1 every year, or you have to pay $1 every year, and so you'd think it'd be 20 times one, $20. But because of that decrease of value of money over time, once you get 20 years out, that dollar is not worth nearly as much because it's 20 years away from now. And so instead of summing to 20, it actually sums to 8.5 because of that steep 10% discount rate. All right, so instead of paying 20 times $10,000 a year for using this good lawnmower, you're now paying only 8.5 times $10,000. So upfront costs, that's today's money, so we don't discount that. We don't discount today's money. But we discount this future money based again on interest rates and number of years it's going to operate, and we get this present value for this good lawnmower of $88,000 something. Now the premium costs more up front, but it costs less to use each year. Yes, we have to discount that, but we discount it by the same rate and terms because we assume they both last 20 years. And it costs overall, over the course of its life, slightly less, even by discounting this annual operating cost. So the premium motor is the better investment with a net present value, net meaning the good one minus the premium one, net present value of $1,135. So what all this math says is that we can think about how much something costs today, and we can think about how much it's going to cost to use over time, and we can recognize the fact that future payments aren't as important to me because they're far in the future, so we can discount those future payments, and then we can still say which one will over time be the better investment, which one is the smarter purchase. And in the case of these big lawnmowers, it's better to spend more today to save energy because your operating costs will be lower over time. And ultimately, over 20 years, you will have saved yourself $1,135 if you got the premium mower. I don't know who actually thinks this way. I don't know who buys lawnmowers. All right. So that was one financial analysis that we will use in this class. And the other one that we'll actually use more often is something called the capital recovery factor. Okay. So it's the inverse of the net present value function, but it has a little bit more utility because it tells you how much you have to pay per year for something. Not what the total value today is, but how much you'll have to pay for something over time. Because that's how a lot of things actually work. So when a city or a company or even a homeowner considers investing in a new technology to lower greenhouse gas emissions, they often borrow the capital cost from a lending company, so a bank, right? This means interest or discount rates. Even if they have the capital, they will likely compare it to other investments and other what-ifs. Some millionaire that wants to buy a house may decide to still get a mortgage even though they could pay for it all up front because they say, well, mortgage rates are only 3% and I can make maybe 7% per year in the stock market. So I'll still take a bank loan and make more from my stock market investment rather than the losses I would get from the interest rate from that bank loan. So even if people have the money, companies have the money, they still take out loans because often they can make more money with the money they have, with the cash they have on hand. All right, so we can convert the capital cost of some purchase into a loan that requires annual payments. So the annual payments A depend on the purchase cost, right? Like the cost of the house or water heater or whatever, multiplied by this cost recovery factor. And so this cost recovery factor takes into account the interest rate and the number of payments that need to be made, and takes into account this time value of money. And so it's saying that these annual payments in the future actually have will be slightly greater because that future money backcasted to today is going to be a lower value. All right, so let's go through an example to hopefully it makes sense. So let me check the chat, make sure nobody's saying anything. No. All right, so capital recovery factor is just the inverse of the net present value function. And so we have interest rate, 1 plus interest rate to the number of years compounded over 1 plus interest rate, number of years compounded minus 1. Again, this funky look to it just comes from collapsing that series into a function. All right, I don't understand this stuff very well myself, so whenever that happens, I just start graphing functions and mapping them to see how they work. So I took D and N, or interest rate and N, number of years compounded, and made this little Excel sheet to see what it looks like. And so at a discount rate of like 10%, and the payment I'm going to get each year is $1. In terms of today's money at an interest rate of 10%, 2 years from now, I would say give me 58 cents today rather than $1 2 years from now. Or give me 12 cents today rather than $1 20 years from now. And so we can see that as time goes on, that value of the dollar decreases for today's worth. That makes sense, right? And then as the interest rate goes up, then that value of the dollar goes up because it's just a higher interest rate. So the annual payment will have to be greater because you're paying more to interest than you are to the principal. All right, so let's go through this little thought experiment. You lend me $1 to make it worth your while. You set an interest rate and a time. So how many years, what interest rate? My annual payments go up with steeper interest rates. That makes sense. The loan is more severe, so I have to pay more annually. And it also goes up with shorter timescales. Now, why does it go up with shorter timescales? It's because I have to pay that loan back much more rapidly, right? Instead of paying it over 5 or 20 years, I'm paying it in 5 years. So that payment divided by the number 5 is going to be much, much bigger because it's not being divided by the number 20. So the total I pay back goes down with shorter timescales. So if we added up all those payments, it actually goes down with shorter timescales because I'm not paying interest as long. And obviously it goes down with lower interest rates. So say I want to buy a super nice guitar for $1,000 from you, but I don't have the money. You graciously say, no problem, you can pay me $160 a year for 10 years. So that total amount is $1,600. So the guitar, increased, the total amount I have to pay increased by 60%, but I don't have to pay it today. I can slowly pay it over time. And so what interest rate does this correspond to? You can answer in chat or directly. So we know that the loan is 10 years. What interest rate does it correspond to when a $1,000 guitar now, instead of paying $100 a year, I have to pay $160 per year? So somebody entered. So I got one guess so far. That's right. Anybody else? So I'll give you a hint. We know that it's a 10-year loan. So it's got to be somewhere down this column. What CRF, capital recovery factor, multiplied by $1,000 yields an annual payment of $160. 1,000 times something over there equals 160. Yeah, okay. I'm starting to get some correct answers. All right, so annual payment is $160. We know the capital is $1,000. So 1,000 times 0.16 is going to equal $160. So it's confusing. You'd want to think that it's 0.1, but that would mean there was no interest rate at all, because that would just be 1,000 divided by 10 years would be $100. So 10-year loan, CRF of 0.16 multiplied by $1,000 equals $160. And so this interest rate that this person with the guitar is setting up, he's saying, I'm going to charge you a 10% interest rate, which is pretty steep. Must be a pawn shop, not a friend. Pawn shop's probably worse than that. Okay. To calculate CRFs, you can play around with this function in Excel called payment. Maybe I'll do that now. Stop share. Screen share. Oh, this is the homework 2 cover sheet I was working on. Anyways, it'll work. All right, so we can say equals payment, and then you type in the rate. So like
this is giving you the capital recovery factor, or giving you?
Yeah, it's giving you the CRF, even though it's not called CRF, and it's because
Okay,
you geek it. So what this function does is, so if you look at these terms, I know this is probably small. You put in the interest rate. The N per is number of payments. So this would be like number of years. So we'll put an interest rate of 0.1. Number of years would be 10 in this example. And then the present value is the present value of whatever you're buying. So like the guitar, so $1,000. If I hit enter, it says I have to pay like $162 per year. And it's red and parenthetical because it's a payment that I have to make. That's the way this function in Excel is set up. But you can cheat it, you can hack it by saying what's the cost recovery factor, and the cost recovery factor is something that's multiplied by every dollar of the principal. So interest rate 0.1, number of years 10, and then the cost recovery factor is just 1. But I don't want a negative number, so I hack Excel and put in a -1, and I get a cost recovery factor of 16. Or you can just do the math yourself. You can just do that equation. I think the best way to get an understanding of this is to play around with it and try to wrap your head around why the annual payments go down with extended loans. That's because you don't have to pay as much each year because you're paying for more years. And why the payment goes up with steeper interest rates, because the interest rates are higher, so you're paying more to interest than principal. Or you can do what I do and just use it as a tool. Like, just be like, okay, this is a little funky, but it works, and so I'll either use the Excel function that I've displayed here in this PowerPoint, or just hand code the math, with a calculator. All right, let's go through an example, and hopefully things will start to make a little more sense over time. All right, so efficient air conditioner. An efficient air conditioner costs an extra $1,000 compared to a cheap one. So that's that delta principle, delta upfront cost. So maybe it actually costs $6,000, but a crummy one costs $5,000. It saves $200 per year in electricity consumption. Oh man, I lost my chat. All right, it saves $200 per year in electricity consumption. So even though it costs an extra $1,000, it saves $200 a year. So, the stupid simple payback would be $1,000 extra divided by $200 per year. It'd say it pays for itself in 5 years. It was purchased with a 10-year loan at 7% interest. So what are the annual savings based on this interest rate and this loan term? What is the ratio of annual benefits to annual costs? Annual benefits would be the savings, and the cost would be this loan that you have to pay. So first we'd calculate that cost recovery factor, interest rate 7%, loan term 10 years, run through the math, we get a CRF, cost recovery factor of 0.14. So the annual payments will be the upfront cost, the delta between the good one and the bad one, $1,000, multiplied by this cost recovery factor. How's it going, Eloise? Cost recovery factor, and we see that it's $142 per year. So the annual savings will be the $200 you save in energy costs minus the $142 you have to pay every year for loan. And we can see that this this nicer air conditioner, even though it costs an extra $1,000 up front, actually saves us in present value dollars $57. So it's a wise investment, because even though we have to pay more up front, we save money each year. Even when we discount that future money savings, because we'd rather have money today than tomorrow, we still realize that we're saving money by investing an extra $1,000 in that better air conditioner. And again, so notice that by annualizing the cost, the buyer makes money every year, so the notion that a 5-year payback period might be considered unattractive becomes irrelevant, because with this loan, they're actually paying less each year in their loan than they are in saving energy. So they're making money even with that loan put in. So that benefit to cost ratio would be 1.4. So you want that number to be above 1. If it's less than 1, then you're losing money. So that's why people calculate that sort of thing. Cool. What time is it? I guess I watched 10:42. Any questions so far? Stuff's tedious, but it's how we do this analysis. Okay, so this is right above my head right now. I have these solar panels on my house. So I bought 5 kilowatts of panels, and it's estimated that it'll produce 4,837 kilowatt hours per year. I think it's going to do more than that, because I've already made like 1,400 this year, and it's only April, but we'll see. It's been a nice April. So I want to see how this compares to the electricity I purchased from Puget Sound Energy. Did I rip myself off or not? So the cost per kilowatt hour of electricity is something I want to calculate. Now, they are warranted for 30 years, so if one breaks, I get a new one. So that's definitely going to happen. My mortgage rate that I pay for this house is 3.6%, and so that's the estimate I'm going to use, the discount rate I'm going to use, because I could have paid down my mortgage for it further or bought these solar panels. That's the choice I made with the money I had. So the cost recovery factor is that mortgage rate of 3.6%, and then the panels last 30 years, so that's the number of payments I'd have to make at that mortgage rate, and the cost recovery factor is 0.06 per year. And so the annual payments I'll have to make over 30 years, I'm not actually making these payments, I paid it all up front, but the money that I need to compete with, if I just paid down my mortgage by $10,000, is this. So is the upfront cost $10,000. It actually costs like $15,000, but there's this federal tax credit for clean energy that you put on your house. So the government pays for 33% of it. Doubt that's ever going to happen again after the government goes broke this year. So here's $10,452 upfront cost multiplied by the cost recovery factor. And so in essence, these solar panels cost me $627 per year over 30 years. But they generate all this energy, and that energy is free. So, well, the energy is not free. It's part of this cost, right? So what did I pay per kilowatt hour? It's $627 per year divided by the number of kilowatt hours it generates. And I can see that my cost per kilowatt hour is 0.13 cents. So yeah, I ripped myself off. PSC Energy is like 0.09%. If you go their green direct program or green power program, where you say that I'll pay extra money and you give me kilowatt hours from wind farms, then it's 12 cents. So it's not too bad. And I don't know if that green power program's real or not, whereas I know that the sun hitting my roof right now making electricity is real. So I feel good about that. And I'm basically paying an extra penny per kilowatt hour to virtue signal. I don't know. No, that I'm being facetious. But that being said, people like virtue signals, and so this actually increased the value of my house. This is kind of the work that Sharon Schumacher does in the economics department. She says, what is the value of green technologies? And so it's estimated that this added $8,500 in value to my house. And that's not just me making that number up. That's what my insurance, my home insurance assumed. And so if that really did add $8,500 to my house, that means if I sell my house, I recoup a lot of that upfront cost. And so then the annual cost is only $120 and my power is 2 cents per kilowatt hour. So that's amazing. So depending on how you look at the investment, it's either kind of a wash or actually saves me a lot of money. So, and the carbon intensity of my electricity is now 0, except for scope 3 emissions from building the panels.
I mean, isn't 13 cents like the average United States per kilowatt hour charge? So like had you put this almost anywhere else other than Washington and probably the Northwest, you would have been at least even. In Hawaii, you'd be very happy.
Yeah, definitely. That's an excellent point. And furthermore, electricity costs will probably continue to go up in time. So,
but that
mine
13 cents for you is flat. Yeah.
It's flat.
So small benefits.
Yeah. It's not the best investment, but it's something I feel good about, and putting my money where my mouth is, right? Okay. If I try to convince all of Bellingham to switch to solar panels, I better have done it myself before I make that call. Okay. Cost of saved energy. So we kind of played around with that in the last slide. Ethan wrote, it says it adds $8,500. That's in today's dollars. Yeah? Yes. That's in today's dollars. And honestly, it's probably in like last month's dollars or 2 months ago's dollars. Who knows what's happening with home prices now? It's probably all going to go down significantly. Kind of needs to. I mean, I'm like one of the only millennials I know that actually is able to afford a house, and that's because I married a doctor. And your generation is even more screwed than mine, so I'm happy that the housing market might collapse from all of this. Okay. So the cost of saved energy measures the cost of efficiency measures in the same units as one compares energy supply or resources. So we're trying to say, okay, I made my house more efficient, or I bought solar panels or something. Let's use math to put the dollar savings in terms of energy unit. That way I can compare it to power bills or gas bills. So the cost of saved energy is a levelized cost of energy saved. That means that we use the cost recovery factor, levelized it over time to annual payments. And it should be directly comparable to the levelized cost of energy supply that we use. And so what you pay PSE in your power bill is already levelized. They said, okay, we have these operating costs, these investments we're making, these purchases we're making, and we make this much electricity and we want to make a teeny bit of profit. This will levelize it all, discount it, and it equals 9 cents a kilowatt hour or something here. So the cost of saved energy is the ratio of levelized annual cost of efficiency measure or program to the annual energy savings. Let's look at that a little bit. So the cost of saved energy equals that annualized cost, LLCC means levelized lifetime cost, life cycle cost, levelized life cycle cost. And it's not life cycle like scope 3 emissions, it's life cycle in terms of financing. Levelized life cycle cost is dollars per year of that efficiency measure, which does not include the cost savings from the reduced energy. That's the benefit. So you take the cost to the benefit divided by cost, like we did with the air conditioner. And the life cycle costs are mostly one-time upfront capital costs, but they can also include operating costs that occur annually. Operating costs of efficiency measures usually don't even come into play. Like if you insulate your house, it's all up front, right? You don't have to pay something every year to operate your insulation. Okay, so the levelized cost to save energy is the sum of the annualized incremental capital costs. So that's the one-time payment, the capital cost multiplied by the CRF, plus the net increase or decrease in annual operating costs. So that'd be like the operating costs. And then you divide that number by the amount of money you save each year, or the energy that you save. Not the money you save, the energy you save. That way you get $1 per kilowatt hour, or $1 per gigajoule, or $1 per therm. So, and that way you compare it directly to your power or gas bill. So the estimation of the cost to save energy can be simplified by assuming that the energy savings are a uniform annual series. And so this is what the CRF does. And this is a very safe assumption to make. And so the cost to save energy, $1 per kilowatt hour for an electrical efficiency upgrade, for example, would be cost recovery factor as a function of number of payments. That's going to be how long your upgrade lasts. So a water heater might be 10 years, insulation might be 30 years. And then the discount rate. And then this is the upfront capital cost. Sorry that I changed the nomenclature. I was making my slides all pretty and then I just started typing in PowerPoint. So this is direct capital costs plus direct cost of operating, dollars per year, divided by how much energy it saves per year. So capital costs multiplied by a cost recovery factor plus operating costs divided by the amount of energy you save per year. And that's exactly what I did with this solar panel example, right? Capital cost times cost recovery factor plus operating costs. Operating costs for a solar panel, 0. Divided by the amount of energy I save per year, meaning I didn't have to pay PSE for this energy. And so my cost to save energy is 13 cents per kilowatt hour, or 2 cents if you assume my house value went up. All right. So there it is again. Capital recovery factor, capital costs plus operating costs divided by cost to save energy. Okay, this just says the same thing. So the capital recovery factor, again, depends on discount rate and life of the upgrade. So if the measure replaces other new equipment, replace on burnout, then it's not the capital cost or direct capital cost, it's the delta capital cost. So say I'm buying a new water heater, and because my old one broke, and I'm not going to say what's for the cost of saved energy, I'm just going to look at the delta between a electric heat pump water heater versus a gas water heater, not because I have to buy a water heater anyways, no matter what. Okay. All right, so here's a quick and dirty example. Cost of saved energy, cost recovery factor, delta in capital cost plus operating costs divided by energy saved. So efficiency measures in a truck fleet. So say you're the city of Bellingham and you have 10 trucks that go around town doing various things. But you want to buy a truck that has better mile per gallon because you know that'll save you fuel costs. But the truck with better mile per gallon is made out of aluminum, not steel or something, and so you have to pay an extra $1,000 per vehicle. And so efficiency measures in a truck fleet at a cost of $1,000 per vehicle, but they save 100 gallons per year in fuel for that fleet. and also save $10 a year in operation and maintenance costs. So at a discount rate of 8%, over 10 years, the cost recovery factor is 0.15. And so the cost of saved energy is cost recovery factor multiplied by not the capital cost of the truck, it's not like $50,000 here, just the delta, so $1,000. Minus 10, that minus 10 comes from savings in operations and maintenance. So CRF, capital cost, delta capital cost, and then operational costs. And operational costs in this case are actually negative, so that's why it's a negative sign there. And then that's divided by the amount of energy that's saved, 100 gallons, and the cost of saved energy for this upgrade is $1.40 per gallon. Again, why do we do this? It's so that we can compare it to the actual price of energy. And, well, in Colorado right now, gallon of gas is like $1.20. Nice. My dog is eating my daughter's breakfast right now. Okay. Lectures from home. So here, I don't know what price per gallon of gas is right now. I haven't driven my car in like 5 weeks or something. Say $3. And so here, this investment makes a lot of sense because it's essentially you're paying $1.40 per gallon of gas by making this efficiency upgrade instead of paying $3 per gas. Starting to make a little sense?
The 100 is the change in normal operations, which is DCOP from earlier, and then ES is
energy saved.
Okay.
Yeah. Sorry I got so sloppy with my math. Okay. Let's do another example. So LED example. This is an efficiency measure, right? Swap out old light bulb for an LED. An LED runs off of 15 watts. You can get even smaller ones too. And it lasts for 20,000 hours, so a lot longer than an old incandescent light bulb, which is literally burning a piece of metal, and that's why they break eventually. It costs $1. So it replaces incandescent light bulb at 75 watts, and the incandescent light bulb only lasts 1,000 hours, and they're only 50 cents each. So this $1, you get one light bulb, and that's why I have that 2x here, because you can buy two light bulbs of the chromier kind. So we actually use the light 2,000 hours a year. So I don't know, there's 60 hours in a year, so we're using it a little less than a quarter of the time. Seems excessive, but that's what I put in this example. And so it'll last 10 years. Oh yeah, that's why I did it. So I could just do 20,000 divided by 10 is 2,000. So it lasts 10 years, and it will replace 2 incandescent light bulbs every year, because these 2,000 hours means that this old-fashioned light bulb will pop halfway through the year, and you have to put in another one that will pop again at the end of the year. And so it lasts 10 years and replaces 2 light bulbs a year. So let's look at the cost recovery factor. 10 years, let's assume an 8% discount rate. It's 0.15. This is just what I see all over energy literature. 10 years, 8%. 10 years, 8%. I think that 8% is kind of matched to the traditional returns that you get from the stock market. So you could say like, oh, I'm doing this, or I'm just going to invest money in the stocks. So the annual cost is CRF multiplied by $1, because that's how much the LED light bulb costs. That's the capital cost. But it's the delta, right? So minus 2 times 50 cents for the other one. And so it turns out to be 50 cents per year. The annual savings are 2,000. No, I did not discount the incandescent light bulbs. And that's because it's not something that's going to last 10 years. It doesn't even last a year. So I have to pay that annual cost every year. So the annual savings are 2,000 hours. Remember, time times power is energy. So 2,000 hours times power, 75 minus 15. That's the delta in power consumption between an incandescent and an LED. And so I save 120 kilowatt hours per year. So the cost of saved energy is 50 cents. That's the annualized cost, or the levelized life cycle cost, if you prefer that language, divided by 121 kilowatt hours. So 0.004 cents per kilowatt hour. This is way, way less than retail price. I made this graph back when I lived in California. So this is way, way less, even with our lower price of 9 cents. It's still like a ridiculously good investment. This pays for itself nearly instantly. And I often hear people say, like, well, want to see what's going on? I often say, like, people say, like, why would I get rid of a light bulb that already works? Like, I already paid for it and it works, so I'll wait for it to break and then I'll get an LED. But it's stupid, because you're actually pissing away money the whole time with that old light bulb. And just by getting rid of it, you'll start saving money instantaneously. And so this is where this kind of thinking actually is really useful in convincing, companies or the public to make a decision that will actually lower greenhouse gases and also save them money. I don't think I want to get into this kind of stuff. This is all that we've been doing, but I just was typing all the formal mathematics and language for it all. And that's basically the end of today. All right. So that was a lot of economic analysis, but hopefully a couple examples: lawnmower, fleet, light bulbs, my house, helps make some sense out of all this. And these are the sorts of tools you'll have to use, even in the bubble water example. We do a simple annualized cost for the soda stream in that homework. So have a look at that, play around with the homework, and see if you can start to have it make some sense for you. How effective is cost of saved energy? Sorry, I'm reading another comment from Ethan. How effective is cost of saved energy with a fuel with a very variable price in the long term? Talking about gas in the previous problem. Oh my God, yes. So people geek out on this like crazy. They'll make like Monte Carlo statistical models for where gas prices or fuel costs are going to go. And it's super important if you're a power plant operator, right? If you run a natural gas power plant that's going to last 20 years, you're going to be very concerned with how gas is going to vary over time. And so you have to make models, right? And have different distribution functions for the price of gas over time, and then run the calculation again and again and again, and try to get a range of what your annualized operating costs will be over time because of those variable fuel costs. If you want to go into the details, read that chapter from Gil Masters, chapter 5 that I posted to Canvas. He spends several pages on that sort of thing. But it's beyond the scope of this class, because we're just trying to basically get to the quick answer. Is this a meaningful, a low-cost way to reduce carbon, or even a way to save money to reduce carbon, or is it prohibitively expensive? But excellent question. Another question I got from Ryan. So would you say CSE is the most useful for this class? I would say that certainly for efficiency measures, it's the most useful, where it's something that you're reducing your energy costs. It's obviously not going to be useful for other carbon mitigation measures, like turning Railroad Avenue, for example, downtown to a walkable street, because I don't know how you'd figure out what energy got saved or something like that. And so that you just use direct dollars. you'd say how much dollars does it cost, or in that case probably gain, because the businesses there will. It's been many studies have shown that you actually increase restaurant traffic and store traffic on walkable streets compared to parking streets. And so yes, it's problem dependent. Cost to save energy is very useful for this class, and the most useful function is just that CRF function, and that allows you to annualize costs over the lifetime of a project. So you can say how long something's going to last. And if it's a city project, you'd use like a municipal bond discount rate, which is about 5%. If it's a home project, you'd use like a mortgage rate, which is like 3 or 4%. If it's a corporation, then you'd probably want to use more of like a stock market rate, like 7-8%. But yeah, CRF is definitely the most useful thing in this class. It's all a bit of a dark art, at least to me, this economic voodoo stuff. Other questions? All right, well, I'm doing a good job of checking my emails. You want to say hi, Violet? I'm doing a good job checking my emails, and we'll meet again Thursday, where we'll learn about the marginal abatement cost, and that's the last like technical thing we need to learn for this class, because we need to understand how much does it cost per metric ton of CO2. So Thursday we learned how to calculate carbon. Today we learned how to calculate money. Now we can put it together and get dollar per unit carbon, and that's what we're going to do Thursday. And then Tuesday it's Carbon Hackathon, so we won't meet, but I'll still respond to email. And then the following Thursday we'll work on the bubble water homework together. Sound good? All right. All right. Thanks. Yeah.
Just thanks.
Okay. Cool. All right.
Have a
Be
good
well.
one. Likewise.
Really. Bye.
Thank you.
Bye.
How many people weren't there?